much to the organizers. I have to go fast because I prepared the 3 hours note, but I have 15 minutes, so I will move. So this is the acronyms of our project. It's apace. It's about the solar pump lasers, which works with unconcentrated sunlight based on photosynthesis. Antenna complexes, I will tell you what is the idea about. Very quickly, the consortium, we have 10 units. There is the coordinator is the University of Florence, and then there is also CNR, ARMA. I don't want to mention the 𝐏𝐨𝐼𝐞𝐬𝐬 Institute. There are too many to mention, but last but not least, there is also we have a graphic designer team that made this animated logo, and these are called 𝐏𝐸𝐫𝐶𝐬. They're very nice, very hardworking. Okay. So they also help in the project. Let me move on. Okay. So very quickly on this, because you already know there is a huge energy demand for space activity in the near future due to mega constellation of satellites. We know many companies want to do that. Space-based power station. The Artemis program that wants to build a base on the Moon and on Mars. So the problem, we need energy, but we also need self-sustainability. We need the energy to be produced in situ, because we cannot send, like called the grocery store, if we need something on the Moon or on Mars. And let me say a topic that has not been discussed at all in this conference, which is a laser power transmission, which space to space can be very effective, because laser have a high density, smaller transmitter and receiver aperture, and lasers can be used for communication, quantum key distribution, sensors like LIDAR, optoelectronic devices, so nano laser, micro lasers, and in cities energy production. And how lasers are done in space typically is that you take the energy from the sun with a PV, a photovoltaic panel, then the electricity pumps a diode lasers, and diode lasers pumps typically a solid state laser, and then the solid state laser sends a beam, because diode lasers have a beam quality very low, so you need a solid state laser. As you see, there is a lot of passages, a lot of electronics, right? So if you can take sunlight directly and turn it into laser light, without electronics and diode lasers in the middle, that would be very good, okay? Now, in situ energy production with the laser, this is the magic cycle, for instance, that uses magnesium. The Moon is full of magnesium, for instance. So you can deoxidize with a high power laser. That's an idea of Japanese idea, Yabe, that we build a solar pump laser in order to heat the magnesium high enough in a concentrated way, so that you can create a total renewable cycle and create energy in situ. Magnesium has the same caloric power of carbon, or just around it, okay? So lasers can be used also to produce energy in situ. Okay, what is the idea of Apache? Apache wants to build a solar laser not with natural sunlight. So you take unconcentrated sunlight and you produce a laser, okay? Without the use of lenses, without the use of tracking devices, because usually solar lasers exist since the 60s, 2 years after, the laser was invented, they built a solar pump laser. What they do, they concentrate sunlight with a big lens, and then you need to, you cannot concentrate diffusive light, so you need to follow the sun, right? Then you reach thousands of Kelvin on your laser medium, you need to pull it down and so on. The efficiency they reach in this way is 4%, okay, but it's very heavy, it's very cumbersome to do that. So how we want to reach sunlight with a concentrated sunlight, so solar laser with a concentrated sunlight. So photosynthesis is a great nanoscopic machine that collects sunlight and transports it in the right place with basically unit efficiency. Okay. So the idea is that we will use this photosynthetic antenna and we put these laser units in the right place of the photosynthetic antenna by organic chemistry, and in this way we enhance the cross-section, absorption cross-section of the lasing unit, and we prove that theoretically that this will lead to lasing on the one side. So the photosynthetic unit we want to use are bacterial photosynthetic units, because bacteria are the most efficient photosynthetic unit. Bacteria can be grown on the space station, it has been done already, and extraction of the antenna from the bacteria is not a difficult process. Okay? And then these bacteria are able to live very underwater in very low light. And these antennae are almost 100% efficient, meaning that of every photon that is absorbed, go to the right place, okay, without dissipating. Of course, photosynthesis overall is not that efficient, but that part of photosynthesis is extremely efficient. So you see, since sunlight is very dilute, all photosynthetic systems operate with a network of chlorophyll molecules that has to capture the sunlight and transfer the excitation to the reaction center, where charge separation occurs, which basically provides the voltage to the cell that drives all the other chemistry. Okay? This part of the antenna, so the collection of sunlight, or the transport of the excitation, is the part that is extremely efficient. Okay? So, how these photosynthetic antennae bacteria are made of? You see, this is the chlorophyll molecule, and maybe here, and then they self-aggregate. These in green sulfur bacteria, they form huge 200 nanometer, huge maybe 200 nanometer, self-organized chlorophyll molecules, nanotubes, and then these nanotubes are inside the chlorosome, so the energy sunlight is absorbed here and transferred through the FMO, which is another complex, to the reaction center. And they are very symmetric, very well organized. The dipole orientation even of the molecules is very, so every molecule, so this you should understand, because every molecule is an antenna, okay? Every molecule is a little antenna, and it obeys Maxwell equation like any antenna, okay, the transfer of energy between the molecules. Then in purple bacteria, you see that these purple stuff are the chlorophyll molecules. They form this very regular circular arrangement, okay? And these are LH2 complex, they're smaller, there are 18 chlorophyll molecules here. Here there are 36. And they are on a chromatophore, which is a sphere, and the reaction center are inside these big circles. And they collect light very efficiently, okay? So the idea of Apache is to substitute the reaction center with a proper laser unit so that you can increase the cross-section of the laser unit, okay? So, okay, this is a more technical. Basically, the point is that all this symmetry that you see of the chlorophyll molecule, this antenna, each chlorophyll molecule you can think of an antenna with a certain direction, is there in order to have cooperative effects like super radiance and super transfer. And so this is the reason why these antennas are very efficient. Okay. So that's the core strategy of the Apache. So you take your bacteria, this is one, there are many. You take your bacteria, you extract the photosynthetic unit, which is this sphere, chromatophore 60 nanometer long. So we are talking of a nanoscopic machine here, right? So we substitute the reaction center with proper laser unit. Here we put a dye, we can put a solid state based laser unit. And then we place these into a cavity, and I don't know what happened.
It's a touch.
And it doesn't work, right?
No, it's a touch.
Yes, I understand. I'm almost kidding. But I got scared that exactly this point they should have worked, and then it didn't work. No, and then you should laser. So if I don't touch something here, because I'm a theorist, so it's better I don't touch. If I don't touch anything, probably it will work. So that's the general idea. And what are the novelties? Okay. So the novelty of Apache, as you see, in our team, in our consortium, we have basically the only guys already built a concentrated sunlight power, solar power laser, which is the 𝐼𝐏𝐼𝐾 Institute of Technology together with Toyota and in Japan collaboration. They built a concentrated efficiency was very low, 0.1%. When I say 0.1%, I mean of the energy that is coming on the laser, you transform only 0.1% into laser. It was a neodymium-based laser. The reason why this efficiency was so low is because neodymium absorbs very weakly. Okay? And the transfer of energy they used was radiative, so not very effective. The idea is that you put a laser unit inside an antenna, then you increase by order of magnitude the transfer of energy. So the idea is that we can reach between 1 and 10% if successful of efficiency, which would be an improvement to order of magnitude of existing unconcentrated solar energy power. So the novelty is that we use no concentrator, no solar tracking, no electronics, no diode lasers, and it's self-sustained in the sense that the laser medium can be produced by growing bacteria on the space station, which is possible, and extract the antenna, and then you replenish your gain medium. Of course, I mean, this would be the first completely new solar laser that does not exist. So of course a lot of R&D will be needed if we succeed to make it work in a real environment, but certainly to build something that does not exist, that is never brought. I mean, it can be used in a good way. So let's say never brings bad things, but it's not true. It can be used also in a bad way. Okay, that's all.
We have some time for questions. Is there any questions?
Amazing presentation. I have a question about the sustainability of those materials whenever you produce them, because I saw it could be chemical producing or something like that. So how you can compare it with the normal silicon material?
No, look, of course, I mean, there are many steps away from answering in a complete way to your question, but I will try. So first of all, of course, the specific answer to your question depends which laser design we will employ, right? Because according, I showed you one route. We were pursuing several parallel routes, right? The one which succeeds will determine the laser design. So first we need to make a new laser medium, then a laser design for that laser medium, and then see. But by the way, let's say the ground answer. These bacteria can be grown just with a bit of sugar. They don't want oxygen. Then anaerobic. So just a bit of sugar and they grow. You don't need much. They are small things. Okay. So once they grow to a starter antenna is a mechanical process. It's not a chemical process. Basically, you smash them and you make the antenna deposit. Okay. So it's not. You don't need many chemicals. Then at that point you have this solution of bacteria. Now, if you put it in water, then you need water, right? If you put it in PVA, then you will need some PVA. I mean, it depending, you see, these, now we enter a bit into the details, right? Now, how if we want to scale these things up, right? Because these, they absorb unconcentrated sunlight. So you need surface, otherwise if you want power, right? First of all, the demonstrator we are aiming to is in the milliwatt, which is already okay for laser communication, for instance, okay? But of course, if you want power transmission, you need kilowatt, megawatt, right? Then you need a surface, right? Then you can think of these fluid going around with this antenna. Each antenna is a few nanometers, so it's a solution of this nanoscopic machine able to eat sunlight and turn it into a laser, right? So you can collect, you can make a modular things, and each laser for each antenna is collected, right? And so you power it up, you scale the power up. Now, you see that the fact is modular, so you don't, all the heat dissipation, you need, it's localized, right? It's not that you have, in such an area, you have to dissipate a kilowatt of energy, like it nowadays. If you want to have a megawatt, yeah, 90% of the energy is dissipated in it. Then you have the problem to dissipate a megawatt in a centimeters cube or something like that, right? So this is modular, so it's easier to dissipate energy. And you can scale it up, but it would work like a solar panel, but it turns sunlight into laser directly. So this would be the idea. Of course, all the details, protection from radiation and so on, these we're working on that. Take into account that these bacteria have been found to live outside the station. Okay, so there are extremophile bacteria who live in free space.
That was my follow-up question, actually.
No, we are doing experiments about the resilience. There are many things. We will not use directly bacteria, we use the antenna. Of course, some level of protection will be necessary. We are studying temperature variation and so on. But, you know, like also solar panels and everything you have to protect from temperature variation. So this will be an issue. The idea, one possibility is that there will be a working timeline, and then you make this fluid circulate according to the working lifetime of the medium, for instance, in these structures, right? So you're circulating, and so it's a way, that's a typical thing people do with dye lasers. You make it circulate in order that the degradation, so you're exposed for less than it degrades, right? And hopefully you can recover it or substitute it. So this will have to be thought of, but first you need to make this new thing, right?
There any other questions?
Actually, I may have a couple of them. First, there might be a dead rate and a grow rate. So how do you play to manage this?
Well, once you extract the antenna, they are dead. I mean, you don't need to make them live with the bacteria. You you grow them and then you take the antenna, and that's all. They don't need to keep living. Unless once in the future, one wants to use the live bacteria, right, to be. And in that case, it's about genetic engineering, because then you can use extremophile bacteria. They can survive under huge temperature difference in free space, for instance. But this is another route outside the drop. Okay. For now, we use that bacteria, meaning that you make a drop in the station, you strap the antenna in the station, and then with the antenna, you make the laser medium. You don't need them to stay there.
So once then you are using that for later.
Yeah.
How long? What's the lifespan of this material?
Yes, yes. No, this is what I was telling you. This is something, so we need to study. We need to study this. The issue is this. This is certainly a critical point, and you're right. Organic things tend to be fragile, right? But remember, we have organic OLED in the 3D screen. They are also organic. R&D can improve these things, right? So for the moment, let's say we need to do it, and then we need to improve the stability. Let's say there are two different things. We are also studying the resilience to temperature variation, the resilience to space radiation. We have a solar simulator in our consortium, so we will study this. And there are also this will be some new data will come out of this, because this study of this on this kind of photosynthetic material, we are in contact with astrobiology group, and they have not been done. So this also will be a contribution of our project to determine the stability of these organic antenna to the space conditions. But you understand that this is, so if we exploit in the right way biology, this could give us the self-sustainability that we need for our space missions. That's the idea.